Okay, this is very quickly probably going to confuse me because I'm logged in twice now with my desktop where I'm talking to you with the webcam, and then I'm running the LT software, what you see on your screen on my laptop. So you're going to find me looking around not knowing what screen to look at. Okay, so welcome everybody. If anyone has gone all the way through the live session today and the SAAO session and now onto this one, you're a complete hero. This is a long day for you. So it sounds like there's some really successful observing in South Africa. They've got lots of nice observations. And you can see now, this is the webcam in the Canary Islands. So Canary Islands, Northern Hemisphere, it's the summer. So the sun is only really just set around about sort of, what is about 20 minutes ago, something like that. So you can still see the sky is extremely bright. If I can open, this is an all sky webcam. So this is a fisheye lens at one of our sort of neighbouring telescopes, and you can see you know, all around the horizon, various telescopes here, and you can see a very bright sort of glow on the horizon. So it's oh, that's just the screen refreshing. So it's very, very early twilight right now. And so what the telescope is doing is it's taking flaps. It's too bright to the sky to take science data, but it's ideal to take flat fields. So what I'm going to do is briefly, I'm going to sort of introduce you to the telescope first of all, because what it's doing at the moment is not very interesting. It's taking just a series of flat fields. So I'm going to talk a little about the telescope. I'm going to show you some slides and that sort of thing. Then I'm going to show you the engineering interfaces, how I interact with the telescope, or not interact if the case may be. And then we'll move on, and hopefully by then it'll be dark enough that we start to take some science targets. Now, what's if you were in the SAAO session, what's different between that telescope and this telescope is, so David was observing remotely from Cape Town. So he was in his office at the observatory in Cape Town, and he was connected to the telescope in Sutherland, and he was controlling the telescope remotely. Okay, so this telescope, the Liverpool telescope, is not a remote telescope, it's a robotic telescope. It's a fully robotic telescope. It was conceived and designed right from the beginning as being a robotic facility. So robotic does not mean remote control. So we have nobody at the telescope observing during the night. We have nobody at the telescope maintaining it during the day. And similarly, there's nobody in Liverpool who's staying up during the night interacting with it. So what that means is that I don't actually really have control of anything here. So I'm going to show you interfaces. I'm going to show you the engineering interface and how you sort of interact with the telescope. But I'm not controlling anything, and I haven't controlled anything all day today. So all I've done so far, this afternoon, I logged in, I checked the weather, I made sure it was good. I made sure there was no build-up of any sort of dust or clean or things that might adversely affect the optics, and that all the computers were working. And then I clicked one button to say go. And then I've just left it, and the telescope since then is behaving entirely on its own. The robotic controller, it's when it's reached the appointed time and the sun has set, it's opened up, it's powered on all the systems, and now it's taking its own data. So in terms of moving the telescope around, I don't have any control about it at all. And in fact, if I were to take control, it'd only be in the case of there's some sort of, you know, disastrous problem that I need to step in and resolve that the robot can't resolve. So I'm not in control of the telescope. I'm also not in control of the observations. So the robotic telescope has a scheduler routine, and the telescope itself will choose what to observe based on the list of targets that's been given to it by astronomers all around the world that are in its database. So I can't tell it what to observe. I can't do what David did in the previous session, where he put in the coordinates for a target and pointed to the target and took an exposure and he nudged the telescope around to put the star in the right position. I can't do any of that without any sort of extreme difficulty. So the robot is in control of the observations and it will choose what to observe. So the question is, what am I controlling it at all? And the answer is not very much. Now, I'm sort of over-egging the situation a little bit. I can suggest very strongly to the robotic observer what I want it to observe, and the telescope will listen to me most of the time. But there could be situations when we're observing later on when my decision as the human observer would be overridden. So, for example, if a gamma ray burst goes off in about 45 minutes, if we would detect a gamma ray burst with Swift, the telescope would completely ignore what I'm doing. It would drop what it's observing. It would immediately point and observe that gamma ray burst because, the afterglows from gamma ray burst, the optical afterglows fade on timescales of minutes. So the telescope would decide that that is the highest priority science observation to make at that moment in time, and it wouldn't be interested at all in what I thought was the highest priority. It would just go away and do it. That's a good example of time domain astronomy as a rapid reaction at its best, and that's what this type of facility is ideal for. I don't know whether we want that to happen or not. I mean, it would be a nice example of the sort of things that you can do with a robotic telescope. But it would upset our plans a little bit for the things that we want to do ourselves. So I should say, at any time, if you want to ask questions, please feel free to do so. And there are points when probably not much is going to be happening, at which point I'll stop and I'll invite people to give any questions that you haven't asked up to that point. Additionally, you've been posting sort of target suggestions on Slack and that sort of thing. So we'll get to that at some point soon and start putting some targets in the queue. Right. Any questions before we carry on? Okay, let's proceed. So let me see. So I've just got a few slides while we're still in twilight, just to sort of introduce what we're talking about here. So here's the telescope. Here's what it looks like in the daytime. Again, this is inside the enclosure. You can see that the roof is closed in the enclosure here. And here's the telescope in daylight with the enclosure partially open. So you get a sense of the scale here. So this guy standing here, this is Professor Mike Bode. He was the founding director of my institute and really the sort of father of this telescope. So this is a fully robotic telescope. I said it's optical infrared. It's a Rishi-Kreshian Cassegrain design, and it has a 2-meter aperture. So you see this big sort of panel here. This is the mirror cover. Underneath there is a 2-meter diameter mirror. And it's what we call a common user research facility. So it's not got a specific sort of project associated with it. It's not designed for one specific science goal or, one sort of close to science goals. It has a broad portfolio, and we do a huge sort of range of different science. Was there a question there, sorry? I think just someone left their microphone on. Okay, so here is. Hello? Hi.
Can you mute your microphone? Suyesh Gaikwad. Thank you.
Okay, great. Thank you very much. Right, yeah. So in terms of the location, so this is where the observatory is. It's the Canary Islands. So these are the Canary Islands. This big one in the middle is Tenerife, and this island here over to the west is La Palma. So it's this huge sort of volcanic caldera, and on the rim is the Observatorio del Roque de los Muchachos. It's a fantastic site. Here are the Canary Islands, just off the coast of Northwest Africa. So it's a wonderful observing site. It's one of the world's sort of premier sites. And it's, as I say, it's the main sort of European Northern Hemisphere observatory. So there's many major facilities here. So this telescope over here to the right of the image is the 4-meter William Herschel telescope. And this little one right in the background is the largest optical telescope in the world, a Gran Tecan, the Spanish Gran Tecan telescope. Yeah, so telescopes cost a lot of money to run, and most of these are manned telescopes. They have, you know, staff who are based at the observatory all the time, and visiting observers come to the telescope and use the telescope. As I say, the telescope was conceived, the LT, right from the, you know, the get-go as a fully robotic observatory, and it's sort of recognised that the control systems, robotic control systems, were at the point where you could run telescope missions autonomously. So we have a fairly small staff. I've said this before, we're all based in Liverpool. There's no one on the island involved in the telescope at all. Yes, so this is the type of observation we'll be taking. So this is a famous supernova, supernova 2011 FE, and the robotic telescope makes a very sort of powerful tool for this sort of rapid reaction. Here's a kind of example of a classical observing. So this is when I created this slide, this was back earlier in the year. So this was the I've taken it off the website of the William Herschel telescope, which is one of our neighbours. It's a 4-metre telescope. It's classically scheduled. So you can see there's all these sort of nights, and on the night there's a particular observer assigned to a particular science program. So this is you know, night by night by night through January. Got a single science program per night, and this is just a small section of one LT night. And so the point is here that all of these different, where it says prop, this is proposals. This is like a different science program. Different targets, so we're constantly chopping and changing between different science programs. It's not like when David was observing on the SAO telescope. You know, he's got that telescope for the night, and he's got specific science goals. We're constantly changing and looking at different targets. So targets of opportunity, you know, a new transient that night, but then also things like monitoring change on long time scales. So let's say you've got some sort of object that's evolving on time scales of months or years, and you want to take a 5-minute exposure every night for a year. So this is the sort of, you know, sort of monitoring observation that we're kind of well suited to. So we're constantly changing target. Also, we make our data available almost immediately. So we're going to see this as we go on. So as the data comes in, you'll be able to grab it on your computer within about sort of 10 minutes of the observation being taken. So this is very important because we're interacting with other observatories, like, for example, ZTF. We're both reacting to the observations that they make, the detections that they make. We're taking follow-up observations. We're also feeding those observations back to the collaboration so other telescopes can react based on what we've observed. Here's some pictures of the telescope being made. So there's a couple of guys here polishing the mirror, and here's the enclosure. So the whole telescope was built in Liverpool. So Birkenhead is just on the other side of the Mersey River in Liverpool. Which is a large sort of industrial area. It's got a lot of history in the shipbuilding and so on. And so here's the telescope being constructed, and it was broken down into bits and shipped out to the Canary Islands and reassembled. And we've been operating since 2003, with full science operations beginning in 2004. And as I say, from the start, we've been a fully sort of robotic observatory. This is what a telescope traditionally looks like, with a dome, this sort of a dome with a slit. The slit opens and it rotates, and the telescope sees the sky through that slit. We have this sort of unusual sort of clamshell enclosure, so you can see it here. This is it sort of partially opening. So these two sides of the enclosure drop down entirely, so it's fully exposed. So what this means is that we can see the whole sky at once. So the only limitation on our speed is the movement of the telescope. We don't have to wait for the dome itself to rotate as well. So that's great. We also don't have to worry about a phenomenon called dome seeing. So this can particularly affect your observations in the early part of the night with a traditional dome. The air temperature inside your dome is warmer than the temperature outside. So this temperature differential can cause a, you know, a sort of convective current that can affect your seeing. We don't have that problem. We open the enclosure, woof, all the warm air goes instantly. On the other hand, we are exposed to scattered light. So when a car drives by one of these roads, they're supposed to dim their headlights, but not everyone does. And also, obviously, we're more exposed to wind shape and that sort of thing. Yeah, it's an outhouse telescope. So this is how an outhouse telescope works. It's got two axes. It rotates around the base, and then it goes sort of up and down in altitude. And it's also what we call a reflective telescope. So you'll know, I'm sure, that telescopes are refractors or reflectors. Reflectors have a number of advantages. So you can scale them up to be really, really big. in a way that you can't make a really sort of big glass lens and have it sort of, you know, perfect all the way through. So you can make big mirrors, and you can also make, you know, huge sort of segmented mirror telescopes. You remove a chromatic aberration with a reflector. And the particular design of the reflector that we have here is the Cassegrain design. So the light comes in here, it reflects off the primary, it bounces up off the secondary. So you have a convex secondary mirror, and that comes to a focus underneath the primary mirror. So this is what we call the Cassegrain focus. So instruments, cameras on telescopes could be mounted in a variety of places. So on our telescope, all of our instruments are at the Cassegrain focus. So we have multiple instruments on the telescope. So actually at Cassegrain, we have a flat fold mirror at like a sort of 45-degree angle, and that flat can rotate to send the light path in any sort of a direction, in a circle, around under the mirror, and then we have all the instruments mounted round in a ring. So by rotating that flat mirror here, we can select which instrument we want to observe with. So it's a 2-meter diameter mirror with an F ratio of F3. So that means the mirror focuses light to a point 6 meters above the primary, but the overall F ratio of the telescope is F10. This is due to the effect of the secondary mirror here. So the focal length is 20 meters. So that's the distance. So the photons hit the primary mirror, they come up and hit the secondary, and they come back down to the instruments underneath the mirror on the Cassegrain station, and that distance is 20 meters. It's a hyperboloid primary and secondary, and this is called a Ritchey-Chrétien configuration. And this is most sort of major research telescopes these days are built in this sort of double hyperboloid configuration, because that minimizes the aberrations over the field of view. So just to give you a sense of the kind of the physical aspects of the telescope, so we have the top ring up here. This sort of a spindly structure that holds the top ring with the secondary mirror, this is called a serrurier truss. And then you've got the 2 axes of rotation. So we've got the altitude axis, which is running through here. And then the rotation axis, there's a sort of a plate on the bottom that the whole telescope is standing on. So the whole thing rotates in azimuth around that direction. And these 2 structures on either side of the mirror that's holding the whole thing up, these are the forks. So the purpose of the serrurier truss is to maintain essentially the mirrors in alignment with sort of the same optical path. So here, if we have like a sort of simple truss, the effect of gravity. So this is the sort of the big problem we have. The telescope is moving all the way over the sky, and this is a heavy piece of equipment. It's heavy at the top, so you get some sort of sag and flexure as you move. So essentially, what you get is the telescope goes out of collimation. It goes out of alignment between the secondary and the primary with gravity. Whereas the idea of this serrurier truss is sort of a spidery structure here. You have the same sort of sag for both the secondary and the primary mirror, so you maintain the collimation of the telescope. So the mirrors, we have the primary mirror, secondary mirror up here. The primary mirror is in this sort of box here under a cover inside its cell. So the cell is the sort of the structure that supports the mirror physically. Underneath the mirror is what we call the acquisition and guidance box. And so this is what essentially controls, we have in here the auto guider and the electronics for controlling all of the instruments and the acquisition. And then mounted underneath this sort of ring here, these little sort of boxes, you can see these are the instruments on the Cassegrain station. And so inside here is that fold mirror I was talking about. Now, I talked about the 2 axes. I talked about the sort of azimuth and the altitude, but there's actually a third axis on any sort of out-av telescope. You also have an axis of rotation, because with the out-av design, if you were to track a field around the sky, that field's going to rotate. So if you sort of think of the sort of 2 objects going up like here over the course of the night, so those 2 objects are going to be sort of rotating relative to each other. So you also need a third axis, a rotator, in order to take out that rotation, so a derotator, so it rotates in the opposite directions of the sky at the same rate. So those 3 axes together are the 3 sort of axes behind the telescope. This is where we live before we were all sent to work at home earlier in the year. So these are the offices where we control the telescope. This is where we develop our new instrumentation. So we build all our instruments in-house and ship them out to the telescope, and we run operations here. So the robotic control system, so I talked about it being sort of fully robotic and not remote controlled. So the question is, how does that robotic observer decide what and when to observe? So it makes that decision based on a number of criteria. So science users will put their targets into the observing queue, and at any point where the telescope has to make a decision, it has to choose a new observation. It will make that choice based on a number of criteria. So it will make that decision based on science priority. So how important is this target? You know, is it a gravitational wave event that we must observe immediately, or is it a more mundane supernova that if we observe at any time within the next couple of nights, that's fine. Yes, so urgent targets, just gone bang, and then elevation. So as we've seen, targets change their position in sky, their air mass over the course of the night. So it's not necessarily ideal to observe a target as soon as it appears over your horizon, right? Because that's the worst possible situation from a point of view of altitude. What you really want to do is wait for it to get as close to transiting your meridian as possible where you observe it. And then there's also sort of weather conditions. So brighter or less important targets you would observe in poorer conditions, in seeing or sort of light cloud. Right, and then there's instrumentation. So I might just pause there. We'll go back to the sort of the engineering interfaces before I start talking about instrumentation. So let's go and see what the telescope's doing. Right, so it's finished taking flats and it's now taking standards. So I can see that in this interface here. So this is a good point for me to start talking about the various sort of interfaces of the telescope. So we're seeing here sort of, behind the curtain a little bit. So this is the engineering interfaces that only the telescope team see. So in a little bit, I'll show you the observer's interface. So this is the robotic control system. So right here, I can see the statuses of all the sort of the subsystems on the telescope, and they're all green, which is good, apart from a couple of the instruments which are in a variety of different fail states. And they're in fail states for various reasons. So Lotus, this instrument here, this has been decommissioned and actually taken off the telescope. So that's sitting in a box in the office. So that's no wonder it's offline. IOI is our infrared imager. So that is generally got a technical problem at the moment. So that's in a fail state, and it's in a fail state because you look at the temperature. It's at ambient temperature. It's warm. So we've warmed it up because it's got a technical fault. We need to take it apart and fix it, but we can't get out the telescope at the moment to do that. Ringo 3 also, this is a polarimeter. So this is also currently disabled, and the reason is it's in the process of being replaced. So we have a new polarimeter on the telescope that we're currently commissioning. So the old one's been taken offline while we commission the new one that's going to be available in the next couple of weeks or so. But all of the other instruments I've got here, well, all four of them, in fact, are okay. So we've got 2 spectrographs and 2 imaging cameras. So someone asked if we're going to take spectroscopic observations as well as photometry. So I think we will. That's my plan. But what I think we'll probably do is just to keep the data coming in, because a spectroscopic observation takes longer. While we're live, we'll take photometry of various targets, and then we'll queue up some spectra for the telescope to take after we've gone to bed, and then we'll look at the spectra in the morning, unless there's something particularly exciting that anyone suggests that we want to do. So yes, so the telescope is in robotic mode. It's choosing itself what to observe, and it's currently choosing the standards. So once we get to the science group start of the observation, we'll start to see candidates coming up in this page, and it will be ranking those candidate groups, these candidate science groups, and choosing what to observe. If I click on this tab, I can see what it's observed so far tonight. So this is the observation roster so far tonight, and it's pretty dull. It's mostly flats. So it started off here in 1949, and it's taking some sky flats. Starting off with the spectroscopic flats, so it's taking sky flats for our 2 spectrographs, Photospec and Sprat. So obviously for spectrographs, the signal to noise per pixel is going to be a problem because you're spreading the light over a large number of pixels. So for a spectroscopic flat, you need a brighter sky. So you do those ones first. And then it's done it's doing these sort of photometric flats. And it's just moving on now to take some standards. So some of those standard groups have already been completed. So what I want to show you next is just on the LT website. So you can type in Liverpool telescope into your web browser, and hopefully you'll come up with our URL, or you can go to this URL here, telescope.livjm.ac.uk. And if you bring this website up, you can click on this link here under Data Products Quick Look. So if you bring up Quick Look, what this is a list of all of the observations that have been taken over the past few nights. And this updates essentially real time. So when an observation is taken, it will be available on this page for you to download within about sort of 10 minutes of being taken. Now, most of these links belong to a specific observer and a specific observing program. So if I say, right, I want to look at some of Dan's science data, I come up against a username and password prompt, so I can't access it. So the data you'll be able to access is anything that's like a sort of a calibration, so a standard observation, for example. So here we have IRO stand. So these are standards taken with the IRO imaging camera. So if I click on that, I have access to this. This is a couple of nights ago. And I can see all of the FITS files here to download, and also the JPEG images here. So these data are all available for you to grab. Now, the science data we'll be collecting tonight will all come under this proposal ID, JT20A04. Okay, so it's got my name next to it, 20A04. And if you click on, I've taken some observations already in this program in the past couple of nights. So if you click on any group on that line, JT20A04, you're going to get, well, I've already logged in, but you would get a username and password prompt. And the username and password I have posted in the Slack. So in the Slack channel, the live observing channel is pinned, there's the username and password. And this will get you access to all of the data we take tonight. And you'll be able to access it in more or less real time. So within sort of 10 minutes of it being taken, it will be available at this link. The other thing is it will be reduced at this link. So we have a pipeline reduction that happens automatically. So these images have already been debiased and they've been flat fielded. So much of what Dan talked about in the first session, the first science session, has essentially been already covered. So if I can click download the FITS files, or I can click on the JPEG, and I can see the image. Right. So who recognizes this, huh? So this is the the famous sort of pillars of creation in the Eagle Nebula. So I've taken a few images on the past couple of nights. This is just my sort of insurance, just in case the weather tonight was poor. So there's some data already in there. So I've taken this in a few different filters. So there's already some images here for you to do a nice sort of 3-color image of this particular well-known nebula. So you've got the JPEG files, you've got the FITS files. There's also, so I've seen a question, where is the password and username? If you go to the live observing channel, it's pinned in that channel, the username and password. You can also click on this sort of interactive preview and bring the sort of the FITS file up into a sort of a mini DS9. So this is something called a JS9. So the sort of thing you do in DS9, you can do right in your sort of web browser here. You've got this sort of, the various sort of scalings and the zoom and so on and so forth. So you can play around in the web browser there, or you can also download the FITS file to your local machine and deal with it on your machine. As well as the images, there's also some spectra in there already. So here's an example, not a very good example, in fact, because there's been a sort of massive cosmic ray here. So let's see if I've got a better one than that. One that you can see at least. No, that's an image. Yeah, here we go. So here's an example of a spectroscopic observation on the LT. So this again, this is the sort of reduction. You can download the FITS file and have the actual data, but this is sort of like a JPEG preview. So here we have the actual image. So the spectrum of the target is here. So if you've not seen spectroscopic data before, you're going to see a lot of these tomorrow. But we have in the Y, this is the spatial direction, and X is the spectral dimension. So the star is spread along here, and these vertical lines are the sky lines. So here we have the spectrum, non-sky subtracted in green and sky subtracted in blue. And at the bottom, we have the flux calibrated and wavelength calibrated spectrum for this particular object. So there's a couple of spectra in there for you to play around with. So there's a little bit of data here just for you to get started with. So if you just go to J220A04 and then log in with the credentials that I've given you, you can access the data, and then you'll see the rest sort of start to appear here on this particular night as it comes in. Any questions I can answer so far? So I'm gonna have a quick look in the chat because I've seen some pop up. Yep, so let me have a quick look on Slack. Okay, great. I think I've answered the questions that are coming already. So Fiona asked about, are we doing photometry or spectroscopy, and the password and username. So yeah, Dan's answered that one. So I hope everyone's found that already. So we're still taking standards at the moment. So those standards might actually start to appear pretty soon. If I bring this up, I'm going to refresh this. So the flaps are there. Oh, here we go, down the bottom, sort of standards. So I can click here. Oh, okay, that one's obviously a private one, so I won't show you that. I think they're going to appear under this IOO stand when they are taken. The other thing that we can do now, we've got a few standard observations, is the telescope has made its own decision as to how good the seeing is. So it's taken the standard observation, it's measured the forward half maximum of the stars in the field, and it has decided that tonight we have what we're calling good seeing. So that's sort of sub-arc second seeing. So with seeing tonight is around about sort of 0.8 to 1 arc second. So that's, you know, it's really great conditions. So this is the robotic control interface. So I shall just quickly show you the other interface. This is the sort of engineering interface. So it's really, really slow. So apologies for the sort of slow refresh here. So this is actually running on a machine in the Canary Islands, which I've got a VNC session that I'm logged into remotely in Liverpool, and then I'm sending it to you. So this is going to be a bit laggy. But that's okay, because you don't really have to worry what's on the screen, because once the data starts coming in, you can just grab it on your local machine, right? So yeah, so here you can see the sort of overall status of the observatory. Now there's green lights all over the board, which is good. Everything's working. In the top left-hand corner, it says warning, which suggests there's a problem with the telescope. Now that's okay, I know why it says warning, and it's nothing to be concerned about. So I'm just going to sort of gloss over that. There's some minor little technical issues we have that the telescope is complaining about at the moment, but it's not going to affect our observing in any sort of significant way. So I can see various sort of statuses of the various sort of subsystems. We can see here that the enclosure is opened. The altitude system's actually in warning, so it's complaining because of the altitude axis. And the reason it's doing that is because the way that the telescope is working, it has an encoder which is measuring its position, and it does that essentially by measuring the position of the axis on a length of tape. And some parts of that tape are dirty; they need a clean. We need to go out there and do some maintenance, probably replace the encoder tape. And it's found a dirty patch and it's complaining. So that's what that warning's about. That's why it's overall in warning, but generally it's sort of working fine. I can see the weather status. So here's the conditions on site at the moment. So these are lovely conditions. It's still fairly warm. It's 18 degrees Celsius. The humidity is low, about 6%. Very little wind, 4 meters per second, and there's no sort of wetness. So these are sort of perfect observing conditions. It's the ideal observing season on the Canary Islands at the moment. I can see the status of eventually, once it refreshes, the telescope axes. So I can see that the telescope is homed for all of the axes. It knows where it is in terms of its sort of absolute position. Here are the encoders. So this is something where if I had to sort of step in and take control of the telescope, something that might often go wrong during twilight is it doesn't home one of these axes very well. And what that will mean is the tracking and the pointing of the telescope will be compromised on that particular night. So sort of thing that the technical team might do during twilight is take control and then rehome the axis just to make sure it knows where it is in terms of position. But it's very, very rare. So we have a sort of setup where every night, while the telescope's starting up, during sort of early twilight, one of our team will be watching it. And that's all we're doing. We're watching it to make sure it's okay, that all the computers start up correctly. And if we have to step in to fix something. And that's rare. So I would say probably someone has to step in to actually do something, maybe sort of one night in 10. And most of the time we're just watching it. And once it starts taking science data, that's it. We turn our laptop off and go to bed. And then we just come back in the morning and see what the telescope's done. See, the nature of the facility that was conceived from the ground up as being a robotic facility, it was designed to be sort of self-healing. So we have all manner of computer systems, computers watching other computers, and if that computer stops responding, then this one reboots it and so on. All these types of subsystems to keep things operational. And in general, we try to touch it as little as possible. So even if something fails, the telescope will normally fix itself without any human intervention. It can recognize that the system's gone into a fail state, it recognizes it's a state model, and then it resolves the problem. So here you can see that all of the mirrors. So we have the primary mirror support here. So there's a pneumatic system to support the mirror. I don't know if Dan's on the line at the moment, but Dan will know all about the occasional problems we have to do with tracking, where we see sort of elongation of objects in some of our images. And part of that is due to this mirror support. So we have these sort of three sectors for the mirror that supports it with like a sort of pneumatic bearing. Because essentially if the telescope moves around the sky, this is a very sort of massive, this is multiple tons, the mirror, you need to support the mirror to maintain the collimation as the telescope moves to different positions. So this is one of the sort of critical subsystems, and this is well, of course, this is the most amount of trouble. But everything's going to be working nicely tonight.
So I'm here, but I'm having my dinner, so I'm still
in
the shadows for the moment.
Yeah. Yeah, Dan is, one of our, very active sort of users at Liverpool. So probably sort of every technical problem that we have, Dan is very familiar with those. Hopefully they're not too many to compromise his science data too much.
What Chris is saying is I complain a lot.
Well, I mean, it's actually, this is an important point actually, because the nature of no one being at the observatory is sometimes it's quite hard for us to tell when something's wrong. So it's actually very important for our users to complain, because we can sometimes miss the fact that some sort of subsystem has failed, and it's only when people see weird things in their data that we can actually understand this. So it's very different to a manned observatory where, if you're sort of standing there, you hear something, crunching, and something's wrong. And we have, for example, sort of microphones in strategic places to try and listen for that sort of stuff that, sort of some mechanical system is wearing out. But if you're not there every day, if you haven't got a person there, these are the things that are quite tricky for you to pick up on. So we have we do have a sort of symbiotic relationship with our users. We need them to, quality check the data as it comes in. And that has been very helpful in sort of highlighting problems. So here we have, various other sort of subsystems that I'm monitoring. So one of them that's very important is the oil. So the axis, the azimuth axis is on a hydrostatic bearing. So this requires the oil to be running, and that oil also has to be chilled. So these are all quite critical. This is one of the sort of main sort of technical systems that causes the problem with the telescope. One of the last times I went out to the telescope, I went out to do an oil change on the telescope. So we had a period of extremely bad weather, lots of sort of rain and ice, and there was water that got into our enclosure, and that water got into our oil. And I don't know if anyone's driven any cars where the head gasket's gone or something like that. The water gets into the oil, it changes its consistency, it goes all sort of white and goopy, and if you can repair that, you have to do an oil change on the car. You have to replace all of the oil. So I had to go out and do an oil change on the telescope, which is a different sort of job entirely, because it's pretty huge and it takes a lot of oil. But I really enjoy that. You know, one of my great pleasures is, you know, as well as you know, teaching and lecturing and doing my research, I enjoy, you know, being sort of practical and hands-on, and you know, having an actual piece of machinery to fix. And it's an excellent tool, really. It's a really reliable telescope. I mean, in terms of our technical downtime, it's really low. We lose about sort of 4% of our time over the course of a year to technical faults, which is comparable to a facility where you have, you know, sort of people there to fix things. And that's really good, because I mean, I said, like, some of our technical problems, they are fixed in real time by the telescope. There are other sort of critical failures where the telescope can do nothing but power down and wait for a human to sort something out in the daytime. So when that happens, we lose the rest of the night. Of course, the telescope goes into a safety state, and then we lose the rest of the night. So that can impact our sort of technical downtime. But thankfully, such failures are really rare. And that's a testament to the, you know, the sort of the quality of the engineering team we have, who both, you know, sort of designed all these systems and also maintain them. Right. We are finished taking standards, and we are now taking science groups. So the first one in the queue is a science observation that I put in earlier today. And what I've queued up is it's a near-Earth object. So this is I went on the Minor Planets Center today, and I queued up a sort of a nearby NEO that's moving at a fairly sort of rapid speed, because I thought that's a type of sort of time range observation we've not seen so far. So I wanted to try and sort of demonstrate that. We'll see an object moving in the field. So that's something a little bit different to the, you know, the supernovae and the different imaging we've seen so far. So that's actually going right now. So if I go back to the list here, we should now see some standards. I don't see any IOO standards. Maybe they're going to come later. I can look at these ones. So I'll type in my engineering password to open some of these. So these are some of the stats. So these are some of the observations that it's been taken in the past 20 minutes or so while I've been speaking. So these all look good. So yeah, nice images, nice round stars. If it was a normal night, this would be it now. This would be my rollover as a sort of the technical duty officer for the telescope. This is quite an interesting image. So I don't know if you can see on this one, there's a pattern. You can see a sort of spiral pattern on that image. Can you see it's like a sort of a Catherine wheel? There are these sort of lines here. Does anyone know what that could be? So this is an image that it's already been debiased, it's already been flat fielded. There's obviously something on here that is not sort of on the night sky, and there's a sort of, I don't know if you can see that. If you get the FITS file, you'll be able to see it very, very clearly, but if you can't see it on the image, there's a clear sort of like a sort of Catherine wheel spiral pattern here. And what we're seeing here is the shutter. This is the influence of the shutter. So the shutter is an iris shutter. So it expands like that and closes, but the vanes like a you know, sort of aperture on a camera lens. And essentially what we've got here is we've got a very sort of short exposure, and it's sufficiently short that the time that takes that shutter to open and close means that you've got a different sort of exposure level at different parts of the image. So this would not be an image that's very good for photometry because you have like a sort of a differential exposure time at a sort of significant level, significant enough that you can actually see it over this image. So we recommend a minimum exposure time of, I think, sort of 10 seconds in our imaging observations, precisely to avoid its effect. At that point, the time difference of the shutter, the time it takes for the shutter to open and close, is such that this becomes a sort of statistically insignificant. But you can actually see it in this image, which is quite nice. So what I will do now is I will switch to the observer's interface. So anyone who's used the LT, someone like Dan, will be very familiar with this. So this is the interface that any observer. This is not specific to me as a member of the technical team. This is how anyone would interact with the telescope. So over here we have various sort of proposal IDs. And then under here, we have science groups. So some of these are ones that well, all of these are ones I put in before. So this, for example, is the one that we're observing at the moment. Okay. So if I click on this button, display observing sequence. So this here is a series of commands that have been transmitted to the telescope. So we've got a slew, move to this position, put this instrument in, turn on the auto guider, and then take these exposures. So SDSS R band, 180 second exposure, G band, 180, I band, 180, and so on. And then we get to the end, and we have a total sort of exposure time here of around about sort of 15 minutes. So the way this works is when I specify a science group, so I set up a sort of a timing constraint here, and most of these are pretty simple. So it's sort of like observe this object as soon as you can. Then I have sort of weather constraints. So here, for example, I have an air mass constraint and I have a sky brightness constraint. And then I set up that observing sequence as you saw. So basically the telescope has all of these groups, and not just from me, from all different science users, and it chooses what to observe based on these criteria, like what's the priority, how high is the target in the sky, and so on. So as well as my groups, so this is what I was saying right at the beginning, I'm not in control of the observing. So the telescope itself will choose what to observe, and it might well choose a group that is not one of mine. Now, it probably won't, in fact, it almost certainly won't, because what I've done is I've specified a massive sort of high science priority. So I've artificially put a extremely high priority on this proposal, essentially giving a kind of A+++ ranking, saying this is the most important science observation you can possibly do. And so for that reason, I will always win, I think, that scheduling fight. The telescope will always choose one of my groups because I've told it it's the most important. But in principle, any of the science groups are available for it to pick. And then once I stop putting in these types of groups, obviously it will have the full gamut to observe from all these different observers. But right now I've got an unfair advantage. So it's going to naturally pick my science group first. So some of these are groups I've put in. So this is the one it's observing at the moment, and here are a couple more. So I put these in. These are two ZTF supernovae. I picked these ones because they've got an RA, that means they're very high in the sky at the moment, and they're pretty bright. And also they've got a nice sort of background in the galaxy close by. So there's a good example to practice sort of, the background subtraction. So these are a couple that could be observed. The one it's observing at the moment is this one. So this is as I said, this is a near-Earth object. So I'll just show you sort of one last thing. So I have my targets. So these are my science groups. These are the possible groups, the observation groups the telescope can pick. And then I also have my targets. So here's some targets I put in already. So these supernovae, for example. So I've got the right ascension and the declination, this particular target, as well as the target name. This near-Earth object has got a slightly more complicated target because it's obviously it's moving non-sidereally. It's close enough to the Earth, solar system object, that it has a changing RA and dec. So with this one, if I view it, so here I have a list of times, and here is the RA and dec for that target at that particular time. So basically, when the telescope chooses to observe this group, it will interpolate between the two nearest times and then choose an RA and a dec appropriate for that particular time. So that's a slightly more complicated observation. That's the one it's making at the moment. And once it finishes that one, it will probably start taking one of these supernovae, because this is next in the queue. But yeah, it's still doing that one at the moment, you can see. So once it finishes this group, as I say, within about sort of 10 minutes time, it will debias, it will flat field those observations, and they'll be available for us to view it on the quick look page. And hopefully we'll be able to pick out this, this object, and we should be able to sort of blink the images and see it moving. So while we're waiting for that, so I've done a lot of talking. So are there any questions people would like to ask at this stage? Okay, right, stun people into silence. So yes, so I will have a look at the questions that I can see on the live observing channel. So there's been some suggestions for targets. So what would be great if you suggested a target, if you could also give me the right ascension and the declination as well, and also a sense of the brightness of the target. And that will save me having to look it up independently, so I can concentrate on the actual observing interface. So there's been a suggestion to look at the irregular galaxy IC10 and supernova 2020 RLJ. So yeah, these are certainly good targets that we could observe. So as I say, if you drop in some coordinates, I'll take a look. Fiona asked, is there an opportunity to take anything with MOPTOP? So technically, I'm going to say no to that. So MOPTOP is our new polarimeter. So it is mounted on a telescope. It is available to observe with, but not robotically. So it's not available as an option to the robotic observer. So in order to observe with that, I would have to manually take control of the observing interface, which is going to be a bit complicated. In fact, I don't know how to do it. You'd watch me reading Wikipedia articles on how to do it with this particular instrument, because I've not been involved in the commissioning of it. So I would prefer not to do that. But I mean, I will say, I mean, particularly to Fiona, because she's part of the JMU family. If she has got any particularly good targets that she'd like to suggest for us to take during the MOPTOP commissioning, which is happening right now, please do suggest them and we can add them to the queue. Yeah, so Fiona says she wouldn't know how to interpret the images anyway. Neither would I. Polarimetry is not my bag. But Manisha, who's one of the tutors in the school, she's our MOPTOP postdoc. So she's the polarimetry expert. And one of the things she's been doing is writing the automatic pipeline that will be released when we finish commissioning MOPTOP. Yeah, MOPTOP, if you don't recognize why we call it that, so it's a Liverpool telescope, there's a Liverpool connection, so our polarimeters, they've been called Ringo 1, 2, and 3. So Ringo, because the first Ringo instrument, it distributed the light from each star in a ring, and you would measure the polarization by looking at the flux change around that ring. So we call it Ringo. Also, there's a Liverpool Beatles connection there. So we had Ringo 1, 2, and 3. So the sort of the Ringo 4 is MOPTOP, which is the multiply optimized polarimeter. But again, you've also got that kind of Beatles thing going on. Right, so I've got some coordinates here. So 2020 RLJ. So that's an RA of 23, so it's a little bit over. Let me just have a look. It should be pretty visible, I would have thought. Yeah, so right now that's at a fairly low inclination. So what is the current UT? So it's just around about sort of 30 degrees. So what I might do is I'll put that in the queue. We'll see if it gets picked out. If it doesn't get picked out soon, it will probably be because the altitude's too low, and for that reason it's scoring quite low. But if I put it in the queue, it will mean that it will get observed at some point during the night, so probably when it's closer to transit. So I'll put that one in, and if we don't get the data while we're live, it'll be there for us to look at in the morning. But it's a good example for me to show you sort of how we're going to put a new object in the queue. So I'm going to do a new observing group now. So this is so when we talk about a group, this is like an observation block. So this is a block that the telescope will choose and will execute. So the name of the object is supernova 2020 RLJ. So now I need to create a timing constraint. So there can be various sort of options here. So a common sort of timing constraint I might have is something I want to monitor. So let's say I want to look at something multiple times over the course of a series of nights. I might choose what's called a minimum interval timing constraint. And I would say, observe this 5 times with at least an hour or 2 hours between the observations. But in this case, we want to just observe it once at some point as soon as possible. So that's the simplest option, which is the flexible timing constraint. So I'll say, if I put this up to the 20th, so we have year, month, day here. So basically, at some point within the next 24 hours, I want you to observe this target. So I'm going to create that timing constraint. I can now specify my observing constraints. So basically, if we fall outside of these constraints, the telescope will just ignore it. So if the target's at too low an air mass, it can ignore it. If the sky is too bright, it can ignore it. Happily, tonight it's a new moon, so, and also the moon is set, so it's as dark can be out there once we get into past astronomical twilight. So we don't have to worry about sky brightness. I could also add a constraint on, for example, seeing. I could say only observe when the seeing is better than a certain value. So these are constraints basically to optimize my observation. The more constraints you apply, the less chance your group has of being picked because it's in competition with all the others. So if someone's got a looser constraint, then they'll be picked where your group isn't. But on the other hand, some science observations demand good conditions. So in that case, you know, you put down the good conditions and you hope you have a high sort of science priority, a science ranking that's given by an independent time allocation committee to override your sort of type constraints. So here I'm happy with the default constraints, so I'm going to create that new observing group. So that's appeared in my list there, here. So this is my new group. Now for that, I need to create now the observing sequence. So this is the series of commands that I'm going to send to the telescope. So I'm going to create my new observing sequence. So we're going to do photometry. So I'm going to click photometry here and continue. And here I'm going to set up my observation. So I have my target here. So I need to create a new target. So it's an extrasolar target. I'm going to scroll up because I've lost it now. So it was supernova 2020 RLJ. I'm going to put my right ascension. So this is the point where you might see me do a typo. So if that happens, do shout out. So this is 2301 09.6. And the declination is plus 23 29 13. Okay, so I can leave all these as 0. I can create that observation. What have I done wrong? I've got here a semicolon instead of a comma. Full stop. Sorry. So I create that. So I have my target now up here. I've got my correct target. I'm using the IRO instrument, auto guider. So now I need to put in my sort of observing list. So I'm going to choose to do. Let's just do you know, sort of a few minutes in 3 filters. So I don't know how faint it is. 20 minutes. Right. Okay. I'll do 180 seconds. In G, and then in R, and then in I. So that's my observing list. So I will do continue. And then here is a series of commands. So when my group gets picked by the telescope, it will send this list of commands to the telescope to execute. So it's going to slew, it's going to turn the auto guider on, and it's going to take this series of exposures with this instrument. So that now is live. That is now live in the queue, and it's available for the telescope to pick. So there's nothing more I need to do to sort of you know, verify or send it. So this is now available, and the telescope has just chosen a new group, and it's done that in real time. So when it was making that decision, assuming I clicked execute by then, it had this one as one of the ones to pick. Now it hasn't picked it. It's picked up one of the ones I put in earlier in the afternoon. And the reason is because those ones are at a much lower air mass. So basically, they're much higher in the sky, much higher altitude, and for that reason, they have outscored this one. So what I'm going to do, I'm going to do something extra. I'm going to edit this one, and I'm going to make this one urgent. Now, urgent is just going to give it an extra little sort of boost in terms of priority. You know, I'm saying it's even more higher science priority than the ones I've added already. So that might mean that the next time the telescope makes a decision, that one might win, because I'm saying it's sort of extra super high science priority. Now, do we have any science data to look at yet? Yes, right. So here we go. I've got some images that have come in. So I can click on here, my observing log, and I've got observations of this NEO, P114MEJ. So here are the JPEGs. Okay, they look pretty nice. I have no idea where the object is, but we'll try and find it in a minute. And here I can do the sort of the interactive preview. So I believe there's a fourth image that's going to come in a minute. So I think I asked for a G band, an R band, and an I band, which I have already, the RGI. And I think there is a fourth one that is also an R. So basically, because I'm looking for something that's moving, I did sort of two R's. So I'm comparing like with like at the beginning and the end of the observation. So we'll hopefully see the maximum difference between the two. It's only a few arc seconds, so it's going to be quite difficult to pick up. But if it's not easy for us to actually eyeball, then I've got a really good one from a couple of nights ago that I'll show you to sort of illustrate what a near-Earth object looks like in these frames. So I'm going to wait a little bit longer for the fourth one to come in. It shouldn't be very long. Yeah, all good here. So we're observing this target. So I see that, Thalys suggested another supernova 1A. Right, so yeah, so this is all good stuff. So what I'll do, so I'm going to put these in as photometry, and as I say, we'll queue up some spectra as well. So we'll get some spectra of these. But you know, typically we might be looking at maybe sort of half an hour to take a spectrum of some of these objects. So we don't want to sit here twiddling our thumbs for half an hour. So I'll do the spectra later on in the night. That's right. So I'm going to. Right, so okay, so what I'm going to do here, just to speed things up, is I'm going to clone this group I've already got. So I just created this one, 2020 RLJ. I'm going to clone group. I'm going to ignore that, so I'm happy with it. And I'm going to change the group name. So this object is 2020 RQK. And I'm going to create a new target. SN 2020 RQK. So the right ascension for this one is 16 hours, 0 minutes, 58.4 seconds. And the deck is plus 23, 29. Oh, I'm looking at the wrong one now. 16, 0, 58.4. Yeah, 70. 36, 15.2. Okay. So I've just changed the target here, but I've cloned the group. So everything else is going to be exactly the same. So I will, yeah, so it's urgent as well. So I mark the other one as urgent. I clone the group. So these two are both urgent. So that one, RQK, if I was a betting man, I'd say that's the one it's going to pick out next. So it's currently observing this this ZTF target, ABR FFOM. So we'll let that carry on. Right, so I have now my 4 observations here. So I'm going to download 2 of these. Let me just so the first one and the second one are R-band. Okay, so here's my first NEO observation. So that's quite a nice image. See some galaxies and things. So where is this target? So this was at 2042. Observation began. So I'm just going to look at the if it wasn't a sort of a non-sidereal object, obviously I know the coordinates, so they don't change this much. So they're this one's 1938, 24 plus 69. Be around about that. Okay, so okay, 1938. So somewhere in this part of the image, around about here. So let's now, I'm going to open a new window and I'm going to open my other image. I'm going to blink these. See if we can see this. So somewhere around. So in the right part of the image. So you can see the sort of the cosmic rays in this image coming in and out. Somewhere up here. Ah, there it is. You see it? So it's not moving very far. It's only a few arc seconds over these images. That's this particular near-Earth object. All right. While we're on the subject of NEOs, I will just let me show you another one of these, just because it's such a good one. So while I was at the last growth school in San Diego, I got chatting with Bryce Bolin, who's a PDRA at Caltech, who works on this sort of stuff, and he persuaded me to work with him on NEOs and take some observations of the LT. It's a good example of how, you know, the whole growth concept of having telescopes all the way around the world, you can track things. And he was particularly interested in things that are passing extremely close to the Earth. And look, here is something that is passing extremely close to the Earth. So this is a short exposure. This is, I don't know, 30 seconds or something like that. You can see there's this whole sort of streak because it's moving really quickly. And if I open another image, I open this one, and now I do the same sort of blink, you can really see how quickly this thing is moving. Blink images. So where is it? Where's that streak? Somewhere down here. Yeah, there we go. So check this out. Look at that. This is two images, just a few minutes apart. And this object, so this is from about 2 nights ago. And this passed about sort of 9,000 kilometers away from the Earth. So I think I saw on the Slack, I think this is the closest detection of an object, or you know, one of the closest detections of an object of something that didn't actually hit the Earth. So that's really interesting. So we published a minor planets circular on this just a couple of days ago, following these observations. So this is a a good sort of example of the growth team. We've got not just the LT observations, but observations on other telescopes. This is ETF discovery. So a very nice observation. Can I answer any questions at this point? Does anyone have any questions they want to ask?
Hi, Chris. This is Swayam.
Hi.
So I wanted to know a little bit more about the scheduler. So is there, are you the only one who is sort of overseeing the scheduler, or can there be a possible overlap? Let's say 2 persons are kind of trying to schedule the same source and it gets in the queue. So is there a way to sort of counter that?
Yeah, so exactly, yeah. So the scheduler, basically it creates a score for every group. So let me see if I can actually sort of show you that. So we're back to the incredibly slow refresh here. Oh, that's not just slow, that's frozen, isn't it? Oh, no, no, we are going. It's very, very late. Right, I'll talk while it's updating itself. Yes, so basically, the scheduler will score every possible group in the queue, of which there are, sort of hundreds. And it will create a score based on science priority, altitude, and all those other conditions we saw, like sky conditions and so on and so forth. And it will create a score for every group, and the group with the highest score will be the group that observes next. And every time it's changing target, it will recompute. So for example, if someone has added a target in the queue in the past 5 minutes, that gets in contention. It doesn't work out the whole night in advance. So the question you ask is, what if 2 observers put in the same observation in the queue? Well, if those 2 observers have the same sort of science ranking for their program, then they will get almost an identical score. There'll be a slight difference because we also added like a tiny sort of random number as well, so we don't have anything that's exactly the same. But yes, in that situation, what you would have is you would have a situation when it would observe one science group for one observer, and then it would then probably go and observe the exact same target for the next science observer. So that's actually a bit of an issue. That's something we're kind of discussing because that's obviously inefficient. So people have asked questions like, well, why don't you just observe it once and send it to both groups? And the answer is, well, no astronomer ever is going to specify his observation exactly the same as the next guy. They can have different exposure time, or they're going to choose a different sort of grating in the spectrograph or so on. So most of the observations are fairly bespoke. So we do have this sort of inefficiency where we will observe the same target multiple times. Now that rarely happens because there's so many sort of exciting targets of opportunity that typically everyone's looking at different targets. There are some occasions when there's like a particularly bright sort of rare transient, like 1820-18 Cow would be a good example. This is something that Dan did a lot of work on and made a lot of observations. And there were other groups as well using the LT at the same time observing the same target. And in future sort of gravitational wave observations, this would be probably an example where there'd be multiple groups using a telescope to look at the same targets. So something that I don't really have time to talk about at all is, as well as our current telescope, we're currently sort of in the design process for a new telescope we want to build, which is the sort of a larger successor to this telescope. And in that telescope, we might take a different approach to scheduling. And one of the things we might do is establish like a key science project, which would be a large sort of spectroscopic follow-up program, so that we can maximize efficiency and we don't have this situation of sort of duplicating observations. The situation at the moment is a little bit kind of complicated and political because we don't just also have a single sort of time allocation committee. So as well as the time on the telescope is split between, there's some time reserved for just Liverpool users like me and Dan. There's some time reserved for UK users because a lot of our operations funding comes from the UK Science Research Councils. There's some time reserved for Spanish observers because we're built in Spain. The telescope is in Spain, so we pay a tax, a site fee to be located in Spain to our Spanish colleagues to use a certain amount of telescope time. And there's other packets of time as well. So we can often get these different groups, with different sort of science objectives, all wanting to observe the same target. Thankfully, it's fairly rare. Does that answer your question?
Yeah, but thanks so much for that detailed answer. That helps me a lot to understand this.
I suppose that would be a good opportunity for me to sort of do a little bit of advertising because, I mean, as I say, so we do have time available for all sorts of different observers. So as I say, a large chunk of the time is available to UK observers. So if you're a PhD student at a UK university, you can apply for UK time. Now, a little known fact is that UK time is also available to international users that can't apply for our telescope time via other routes. So if you're not from Liverpool or the UK or Spanish, you could also apply as an international user into that UK time plot. So if you go onto our website and if you look at, there's a page sort of phase 1 here. So this tells you all about how you can apply for time on the telescope. So if what you're seeing looks interesting and you've got a PhD where you might need some data, do look into applying for time. And if you don't want to apply for time directly, think about contacting someone like Dan or me who might like to collaborate with you and use some of our JMU time to support your observations. We're always open to that sort of thing, and I'm always excited about doing new things with the telescope, so just bear that in mind. Right, that's the end of my sort of advert. This is slow to, okay. I don't know whether I'm overloading my internet connection here. These are all blank. Okay, right, it is updating. Right, so you can see here, this is a sort of summary, and you see it's got winner. So basically, this is where there's been like a decision to be made, and there's been a fight, and this tells you which one has won. And sure enough, right, we've moved on. So now we're observing supernova 2020 RQK, which was the one we put in a few minutes ago. So that one won. It beat my ZTF target that I put in earlier, and the reason it beat it was because I added that urgent flag to it. I gave it that extra boost. So we've got that one coming in. So that one, we should have some data for that in around sort of 10 or 15 minutes time. But yeah, so here you can see, and one of these pages, I don't know why this isn't updating when I click on it, but if I was to bring this page up, basically you would see a long sort of list of groups all with the score. But it's not updating. Maybe if I leave it for 5 minutes, it will. Let's see if I've got some data on this ZTF 20 ABR target. So I'm going to go to my quick look page. Oh, yeah, look at that. I've got 8. So here's my observing log for the night so far. So I've got a number of observations here. So I've taken two exposures in G, I, and R. So let's have a look at some of these. So there's the I think even on this sort of rubbish JPEG, I think that's the supernova, isn't it? Let me. So these ZTF targets, I didn't sort of pick them out for being sort of scientifically interesting. I just picked things that were at a good RA, and that there was a nice sort of galaxy, because I thought this would be, you know, a good sort of a test of the kind of background subtraction. So let's see if let me. I wrote down the pages. So what was the name of it again?
20 ABR FFOM.
ABR FFOM. Thanks, Dan. Yes, here it is. So I'm using here the Laser broker. I should probably be using the Gross Marshall, but this just happened to be the thing I clicked on first to have it open. So there's the PAM stars image. Yeah, so here you can see, so these are the, I guess these are the ZTF difference images. So yeah, you can see in these, oh, that's still tiny. So there's the reference image, and there's the image with the target. So you can see the supernova there. So that's the old page. Yes, there it is. Yeah. Yeah, nice. So you can access these yourself and play around with them. We've got the multiple colors, so as well as going the science route, doing some subtraction of that galaxy and trying to extract some magnitudes, you could also go the eye candy route and do some nice 3-color images. Yeah, this is not just updating, is it? So Fiona asks, how fast was that NEO traveling? I don't know. You could look it up on the. There's a minor planet circular. You could Google its name and probably find that, and it might have that information. pretty fast. So I assume you're talking about like that really fast move that I took a couple of days ago. So that actually, when I observed that, that's heading away from the Earth. So we didn't even catch it at its fastest point. So I think ZTF probably caught it on the way in. And then, you know, it takes some time for the planet to revolve before the LT can take its observations. And I think we observed it on its way out again. So
could I ask you a question about the observations you just put in as well? Did you only put in 2 exposures in each filter? I was thinking maybe you do 3 so you could use a median, but do you typically only do 2? Or?
yes, certainly, that would make sense. I'll tell you exactly why I've been putting in sort of 2 and 1, and that's so we can sort of try and get through as many targets as possible.
Yeah, sure.
But yeah, you're right. That would be a superior strategy, you know, to do more like that. So maybe I should put in 3 but do shorter ones.
Although I can say personally, when I take supernova observations, I almost only ever get 1 with LT, because the readout time is of order 20 seconds.
Yeah.
And these supernovae are very bright. And so you incur a pretty big penalty on your observations if you actually get 3. And it's very unlikely that in a short exposure of a minute or so that you'll actually get hit by a cosmic ray. So we just accept the tiny risk rather than tripling our observation time, which is basically what we'd be doing if we always got 3 observations.
Yeah, no, that makes sense too. Thank you. Can I ask, Dan, are you still doing observations of the cow, 2018 cow, or is that over?
Well, it's faded away now. I have debated whether to spend some time getting a reference image for it, because one of the problems we encountered the first time is we don't have reference imaging in non-Sloan filters, and we got data in non-Sloan filters. So at the time, we interpolated between the Sloan filters to do a very rough approximation of the Johnson-Cousins filters, but it would be more ideal to get actual template data in those filters. But it's 2 years old now, and it faded, you know, like a rock. So it's not actually detectable on its own, which is what you want for a template image, of course.
Yeah.
And it is up right now, but this is the last month that it will be up during dark time. Next month, it will be too low to observe when the moon is down, when you want to get a deep image.
We've got an observation of 2020 RQK apparently, so let's have a quick look at that. This one. Ooh, nice. Nice galaxy.
Who can guess what the supernova is?
Well, there's 2 bright spots in that galaxy. I'm not sure which one.
Let's get the fits out and have a look, shall we? Those no, no. Yeah, still none the wiser. Does anyone know?
I know the answer, but
okay, pop quiz then.
Could you move your cursor onto some of the different bright spots so we can see the RA index, maybe? Or that's not
Cheating.
I'll give you a hint by posting a link to the chat. Click on that and tell me which of these stars was not there before, because that page includes a link to the pan-stars image of the galaxy.
Okay, it's the one right in the middle of the one arm.
Yeah.
This one. Yeah.
Yeah. So it's in that interarm region there.
Nice.
So do we know what type of supernova this is? Oh, it was a 1A, okay.
Well, so it's occurring not in a spiral arm. So yes, what kind of supernova would you guess it is based on where it's happening?
Yeah, true enough. It's not from a massive star, so yeah, 1A.
Now, it's not impossible to get a type 2 or a type 1c supernova in a place like that, but you definitely need to be biased in your guess to think it's a 1A, because there's probably not a lot of young stars there.
So did you know that already, or was that just from looking at the pan-stars image previously?
Well, we observed this one a few nights ago, so I remember.
Okay. Yeah.
So I see Juanita is asking about the other point. That's a foreground star in our own galaxy, like all the other things you see in this image. It just happened to line up with the background galaxy.
So do we know how far away the galaxy is?
Well, let's see. If you look at that link I sent, actually, there's not a redshift. What's that?
No, it's 0.
Someone forgot to send the redshift. Okay, let's see if it's in NED, the NASA Extragalactic Database. Yes, okay, so it's here. I can, if you give me the screen for a second, Chris, unless you're about to do something else, I can show
you go for it.
Look up information on supernova.
I'll make you a co-host and then you can.
Okay. Okay, so I sent the link to this page in the chat. This has become basically the clearinghouse for transients worldwide. So it gives them names and stores them, and also provides some handy information. So you can go here, you can get the coordinates that we sent it to. You can see the spectrum that somebody posted to show that it's a type 1A supernova, which obviously, as everybody knows, this is clearly a type 1A supernova, just by glancing at that spectrum. And then it gives a bunch of links here to various resources. And so the one that's useful if you want to know redshifts is this one, which stands for NASA Extragalactic Database, which links to just what it says, the database of extragalactic objects. And you can see here the first match in the catalog is UGC. It's a galaxy catalog, 10157. And here it has the redshift. And so you could work the distance based on that, which is something like 100 megaparsecs is what this works out to. So 300 million light years. And that counts as nearby by our standards, by the way. So if you're a galactic astronomer, that does not sound nearby. And if you're not an astronomer at all, that sounds completely ludicrous. But yes, we call that a nearby galaxy in this business.
Cool, thank you.
Okay, so I'll send it back over to you, Chris.
Okay, thank you. So I'm just confusing myself over which computer to share the screen. Yeah, this one. Yeah, there we go. Just again, just as a point of sort of time domain interest, I want to show you another observation that I took. So this is now sort of 13 days ago. So something Dan mentioned was the long readout time on our imaging camera, which is true. It's about sort of 20 seconds. We have a second imager called RISE, which is a rapid readout. So RISE uses a different type of CCD called a frame transfer CCD. So what happens in a frame transfer CCD is there's two halves. There's an illuminated half that's exposed to the sky, and then an unilluminated half. So what happens is it takes the exposure, and then when it's finished, it shifts all of the electrons across to the second half of the CCD, and then reads those out. And what that means is that second half can be read out while the other half is exposing the next exposure. And that shift is extremely quick. It's microseconds. So essentially what that means is by using that particular type of chip, you eliminate the readout time. Now there are compromises you have to make. The sensitivity isn't as good as our main imaging camera. That's why we don't use it for everything. But this is the type of instrument you would use for things where you're taking sort of moving instead of still images. So the example it was built for is transiting exoplanet. So your planet moves in front of the disk of the star, and you see a dip in starlight. And for that, you want to move it. You want a series of exposures. And you don't want a 20-second gap between every exposure, because your exposures are probably quite short. They are of order of a few seconds, or 10 or 20 seconds. So just to kind of round out all the different types of observation, I wanted to show you an example. So this is an example of a binary star that I observed a couple of weeks ago in collaboration with someone at Texas Tech, I think. So I've got here now a series of exposures. So there's over 240 individual exposures here. So each one was 20 seconds or something. So this is a few hours worth of observation. So I've got these, and I'm going to sort of reduce these with a reduction pipeline for this type of thing. So I'm doing sort of photometry on each one of these exposures, difference photometry. The pipeline software I'm using here is something called the UltraCam pipeline software, and this was written by Professor Tom Marsh at the University of Warwick. So I spent 6 years as a postdoc at the University of Warwick working with this type of instrument, this type of fast readout instrument. And this software is the software that Tom wrote to reduce the data from that instrument. But it's such a good software suite, I continue to use it for other instruments as well. So I'm just going to run this. So this is sort of 2 hours worth of data that's going to reduce in very rapid order. So here we go. These are all the individual exposures. So that's the light curve. So yeah, you can see time down the bottom here, 2 hours worth. What's interesting, as well as getting the magnitude here, so this is a target magnitude divided by comparison. So I'm looking at the difference here between the target and the comparison. I've also got an X and a Y position, so you can see there's sort of a drift in Y coordinate over the course of these 2 hours. I've got a measure of transparency. So my comparison star, I'm assuming, is constant in brightness. And so from that, if I do detect a variation in flux from that comparison, I can infer that there's been some sort of cloud in the field of view. And I've also got a measure of the seeing. So the seeing here is really, really good on this particular night. So here's this data. So if I replot that, just to make it sort of clearer on a sort of non-magnitude scale, here's my light curve. So this is an eclipsing binary. So what we have here is we have a subdwarf star, subdwarf B star. So this is a very hot, compact object with a companion that's a main sequence dwarf star, probably sort of M dwarf. And it's an eclipsing system. So in the middle here, we have an eclipse. So most of the flux in the system is coming from the subdwarf B, the hot, bright, compact object. So here we see the M dwarf passing in front of that object, eclipsing it. And you can see that the exposure times here are short enough to essentially resolve the shape of this eclipse. And from that, we can infer some of the the geometry of the system and understand the relative sort of radii of the objects and so on. And we also see up here, I don't think this is an eclipse, this is a transit. So here we're seeing the the subdwarf pass in front of the M dwarf. So it's not eclipsing it, it's just blocking out some of the light. This is like a exoplanet transit, but it's actually a star that's doing the transit. So we see this dip here, the transit of the subdwarf passing in front of the main sequence star. And the other point of interest is you can see outside of those eclipses, there's also an oval sort of shape here. So it's around about this transit, it's peaked right where this happens. So that, you know, it's humped there, then it humps here. So what we're seeing here is a reflection effect. So the hot subdwarf is heating one side of the M dwarf. So these are close objects. It's a close binary. You can see it's got a complete orbit in you know, under timescales of hours, and so they're going to be tightly locked. And so one side of this M dwarf is being illuminated by the hot object and heated. So you've got a hot side of this M dwarf. And so when we're viewing that hot side, we see an increase in flux compared to when we see the cold side of the M dwarf. So yes, that's just a sort of a nice example of the sort of thing you can do with fast photometry. So where are we? So we're still, so we've moved on now. According to this, we're now looking at my other ZTF target, A, B, Q, Y, Z, Z, I. So it still hasn't picked out that other SN, whatever it was, object we put in. I guess because it's still being beaten by the fact that the altitude is too low, even though I gave it that boost at RLJ. We'll definitely get it by the morning. So what do we think? Any comments or questions? Well, what I might do is start maybe queuing up some spectra of some of these objects we put in. What do we think?
Okay. Again, so I want to know if the software that you showed up, which is tremendously fast, is it like available on public, or is it just like very proprietary?
The light curve software I showed you.
Yes, yes.
Okay, yes, no, that's all publicly available. So if you Google Tom Marsh, Warwick, you will find his website, and on that website there'll be a link to his GitHub, and on his GitHub you can find all his software packages, all of which are very good. There's all sorts of very useful packages he has there that you can use. They're a bit of a pig to install, some of them, because they have all sorts of dependencies, but it's an excellent software suite.
Great, thank you.
So Chris, when you're analysing your data, what programs do you typically use?
Depends on the data, I guess. I mean, I increasingly use Python the way everyone else does, but in some ways I'm a bit of a dinosaur. So I use the Starlink packages for a lot of things. I mean, you saw me use Gaia there instead of DS9, I think, and the sort of spectral reduction and that sort of thing. There are some sort of older packages that I rely on, as and when I need to reduce spectra. Again, there's some software that Tom Marsh created. He created a software called Molly, which I think was named after one of his dogs, and that is an excellent piece of software for looking at time series spectroscopy. So sort of various things you can do with that, and doing things like Doppler tomograms and so on. There's some useful software there for that sort of thing. For light curve modeling, there's a piece of software called sort of L curve, which again is a Tom Marsh piece of software which I use. I use various things as well, and a lot of things in Python, for MCMC and that sort of stuff. The way that everyone does it these days.
Cool, thank you.
Yeah, so I'm going to, okay, so if you see if I click on this RQK, you can see now it says there that the group is done. So that has been executed. If I click on this button, execution history, I can see that there's the time it's taken, it's successful. And I can, if I want to, I can resubmit it for another observation at a later date. What I might do is I'll queue up some spectra of these particular targets as well. So this is just a slightly more complicated group, so I can't clone it this time. So if I create a group SN 2020 RLJ, the J spec, in my flexible timing constraint, as I have been doing. I'll leave all of this the same. So now I need to create my observing sequence here. So I'm going to use SPRAT. So we've got a choice of 2 spectrographs on the LT at the moment. So we have, I'll just show you a little bit of information. Yeah, so SPRAT is this little chap. Very compact instrument, very simple. It's a sort of straight through spectrograph. It's got a deployable slit and grism. So the way it works is it does the acquisition actually inside the instrument. So basically, it moves the slit and the grism out of the light path. It points to a patch of the sky. So here we go. It finds the target. It puts the target on a so-called magic pixel. So here's where sort of spectroscopy is something that's a little bit more complicated as a robotic observer compared to a manual observer. So if you're actually sat in the telescope, you take your acquisition image and you can see your target, and you nudge your telescope left, right, up, down to put your target on the slit. So if we're doing it robotically, that we don't have that interaction. So what we have to do is we have to make sure that we specify the coordinates exactly right. Sometimes we might have to take an image first to double check those coordinates if they come from something like Assassin, for example, where they're not terribly reliable sometimes. And then what the telescope will do is it will put those coordinates on the slit. So it takes an image like this, it calculates a world coordinate system. So it works out, the translation between pixel position and RA and DEC, as we've seen, based on the stars in the field. And then it will use that to nudge the telescope to put the target coordinates in the right position. Again, so note that I say target coordinates rather than target, because the telescope is agnostic as to whether there is an actual star at those coordinates or not. It's going to just go for the coordinates that the observer specified, whether or not there's an object there. So often if you get those coordinates wrong, you can come out with a blank spectrum. The other problem we sometimes have with SPRAT is because this is a spectroscopic format CCD. It's not a big square like you have with imaging. It's a long, thin rectangle. So sometimes that WCS fit can fail because it might be a sparse field where there's only sort of 1 or 2 stars in this field. So it can't do that, and then the observation fails. And then we have to resort to other methods. But it takes the acquisition image, it puts the star or the coordinates on that magic pixel. It slides the slit in. So here we now see our star on our slit. Takes a slit image. That's all good diagnostic. And then it takes the spectrum. So again, here we have spectral direction in X and spatial direction in Y. And then when you reduce that data, you get your object at the end. So that's SPRAT. That's our very popular instrument. It's very low resolution, so it's specifically designed for supernovae. So you don't need a very high resolution for supernova observations because the velocities are huge. So low resolution means very efficient, very sort of high throughput. So we can observe targets as faint as sort of 90th magnitude, or maybe even a little fainter, which is pretty good for a 2-meter telescope. So this is our sort of second most popular instrument now after our main imager. We also have Photospec. So Photospec is a much more complicated instrument. It's a higher resolution spectrograph. It's bench mounted. It's not mounted on a telescope. It's mounted in a big box on the floor of the enclosure, and the light is fed to the spectrograph via a fiber bundle. So the fibers are at the Cassegrain station, and they're fed down to the spectrograph. Fibers, are in common use today in all sorts of facilities. They're going to have some sort of impact on efficiency because they're not going to be 100% efficient, just as any optical element isn't. Photospec is particularly low efficiency, so it's something I don't think any of us on the telescope team are that happy with Frodo in terms of efficiency. It could do a lot better. for the typical sort of target magnitudes we're looking at with photospec is, maximum kind of, 14th magnitude, 15th magnitude. Isn't really that great. But the way it works is you have this fiber bundle. So essentially it's like this. You have this bundle of sort of fibers or sort of lenslets covering a section of the sky. So again, we will put the target coordinates on the right position. Now in this case, we have to do the acquisition with IRO. So we use our imager to acquire the object. So we put the object in the right position in terms of pixel coordinates, using that, WCS fit and nudge again. And then we rotate the flat fold mirror. So the light now is being sent to the spectrograph or down the spectrograph fibers, and then we take our spectrum. So that's how this instrument works. So again, that's a bit more complicated. And yeah, so each one of these fibers, we get a sort of a spectrum for each one of those, and based on those, we can reconstruct the image here, and then also based on the fibers that define the object in the sky, we can calculate our sky background contribution and our target contribution and get the spectrum. So those are our two spectrographs. So no surprises for guessing the spectrograph I'm going to use here is Sprat. It occurs to me I've not checked how bright these targets are since I started doing this. So our RLJ, how bright is that one? Does anyone know?
So one of them is quite bright, and the other one is definitely not bright.
Yeah. Yeah, I remember that.
Additionally, I was going to make a suggestion, which is that someone in the chat, I have to remember who it is, Tom Killestein suggested a new supernova that actually hasn't been classified yet. So we really need to get that one because we could actually put out the classification announcement tonight.
Yeah, I might have AT2020 RML. Yes,
I didn't already get that
one in. Yeah,
okay, good.
Right. So, okay, so interestingly, the telescope has stopped taking science exposures and it's taking a standard. Dan might have some comments on this because we've had conversations in the past about the number of standards we take. So we have actually reduced it, but we do take a certain number of standards. So we've seen the importance of standards for photometry, although not such important today because of the wide field surveys we have. But for our point of view, from the point of our robotic telescope, the standards do serve one very important role, and that's because we use them to measure the seeing. So again, if we measure the seeing now with this standard observation, and we were to find that the seeing has dropped from, currently it's considered to be good, if that drops to average or poor, then suddenly there's all sorts of science observations that the telescope will no longer consider because the users have specified, I only want this to be observed in good seeing. So from that point of view, this is quite important. Now you might ask the question, why can't you measure the seeing from your science frames? And we've tried to do that in the past, and it's less reliable than having a bright target that we know the coordinates of to use the sort of the science frames as they come in. So yeah, there is a science purpose even in the days of wide field surveys for us to take standards. We took a lot more in the past. We've reduced the number due to comments from users. Who knows? Maybe we'll review that again in the future. But right now we're taking a standard. And then I wouldn't be too surprised if after that the next observation is this AT2020 RML because I've marked it as urgent. Yeah. Okay. So
by the way, it's extremely good tonight. As you've probably noticed.
Sorry, say again.
The seeing is extremely good.
Oh yeah, it's beautiful.
About as good as a night as you'll ever get.
Yeah.
Is it programmed to take standards on a periodic basis throughout the night to check if the seeing changes, or
yes, exactly.
It's just doing something unexpected?
Yeah, no, it's going to do it, in sort of intervals for exactly that purpose, to check for changes in conditions.
There's a couple questions in the chat, Chris, if you have a sec.
Okay.
I mean, I guess you're still entering in some observations, so I can take them if you want, but if you have a second.
Yeah, go on, and you take them, and I'll finish off this spectroscopic setup. I'll find out which is the right one.
Okay, I'll always take the first question. So someone asked if any groups use the Liverpool telescope for exoplanets research. So the answer to that is definitely yes. Chris would be able to tell you more about it than I could, but yes, there are proposals to do exoplanet science every year, I think, to all of the large time allocation groups. And so I don't have the latest figures because these fluctuate around from semester to semester anyway, but of order 10 or 20% of the telescope time is spent doing various exoplanet related things. I think normally transit type of observations. Yeah, and there's different groups in different places that use it for this reason.
Yeah, that's exactly correct. Let me see if I can.
Exoplanets that were, so there's a follow-up question about what exoplanets we're the most excited about. So I definitely don't do exoplanets, so I'm not sure I know enough to say. I know, our institute was involved mainly through Chris with the TRAPPIST-1 exoplanet discovery of this multi-planet system. How many planets were in that? 5, 6?
7.
7, yeah, 7 planets in the same system. So LT was used to help confirm them in the big discovery that came out a couple of years ago.
Yeah, we were. I think we were the sort of the third biggest contributor to that. So after Spitzer and the actual TRAPPIST telescope itself, the LT was the next biggest contributor to that TRAPPIST program. And in actual fact, we continue to observe TRAPPIST every season still, because we're using the LT observations to refine the orbits of the planets. So essentially, by looking at the transit time variations, so you've got a multi-body system, they're all pulling on each other. By looking at the transit time variations, you can get higher precision estimates of the masses of the planets in that system. So TRAPPIST is one we do every year. But yes, there are many other exoplanets observations as well. I'm looking for somewhere here. I've got like a breakdown by science topic, I think. Oh, here we go. Yes, right. So this is probably a few semesters out of date now, 2018. But this is proposals we've received by science topic. So you can see it's almost all time domain. It's like the variable sky, but we have a solar system, so sort of near Earth objects and that sort of thing. Planetary transits, stars and binaries, so things like eclipses and so on and so forth. Supernovae, classical novae. Gamma ray burst, gravitational waves, blazars, total disruption events, and sort of other, so sort of galaxy observations and sort of deep observations of galaxies and intergalactic medium and so on. So this is the sort of the breakdown by science area, and the colours here are giving you the breakdown by the group of sort of time allocation committee. So most of our time is split between Liverpool, the rest of the UK, and Spain. So blue here is Liverpool, orange, the orange red is UK, and green is Spain. So you can see, for example, in Liverpool, we're big in supernovae and novae. Supernovae is people like Dan, and then the novae is Matt Darnley leads a very active group on classical novae. One of the members of which is Fiona, who's here in the chat. And then you've got UK, so UK do more sort of planetary stuff. So we don't really have an exoplanets group in Liverpool. It's the one area of time domain that we're not heavily involved in, really. But it's a big sort of UK interest, as well as stars and of course supernovae, as well as many other big supernova groups, as well as sort of blazars, places like sort of Southampton, for example, very much into that. And then our Spanish friends, they're also interested in extragalactic objects, as well as they've got a very active group of like solar system. They do observation, occultations and that sort of thing of minor planets and so on. So there's a big sort of difference in our communities in terms of the type of science they do. So that's the breakdown, but it's pretty much all time domain, as you can see.
What kind of stuff is classed as like the galaxies and IGM?
That's probably like stuff that didn't fit into any of these categories. So, for example, Rob Crane at Liverpool, he's he's a sort of, computational, he's part of our high performance computing group. So he did some really deep observations of some galaxy clusters and that sort of thing, big gobs of time to do sort of really faint imaging, which is not the typical sort of thing we do, but obviously, we can do it just like any other telescope. So that's what sort of went into there. So this is kind of like other, I guess. Right, okay, yes, so I think I've discovered which one was the bright one. So 2020 RQK discovery magnitude was 17.9. So I'm going to change this RLJ spec to an RQK spec. I think, yeah, the other one's too faint.
Although if you were able to do something faint on any night, it would be tonight.
Yeah, I guess so. How bright is that unclassified one?
Spectra of faint things do not look very pretty. They barely look more than noise, even though it might be enough to classify in this case. So let's get a nice bright thing if we can.
Also, we finished our standard and we're now observing 2020 RLJ. So that has reached an altitude where the telescope has deigned to observe it for us. So you can sort of see what I mean when I said that I'm not really in control of any of this. It's the telescope that's making the decisions. All I can do is sort of put my thumb on it a bit. So I'm going to set up my spectroscopic observation for this one, RQK. So this is a little bit different. I start off with a configuration. So I have my, we can choose to, there's not a lot of configurable parameters on our instruments. And there are good reasons for this. We keep our instruments simple with as few moving parts as possible because that minimizes the chances of failure. So our more complicated instruments, like for example, our IOI infrared imager, which has very complicated cooling systems, they seem to spend as much time broken as they do actually working. Something like Sprat, which has very few moving parts and very little configurability, is pretty reliable. So we have one option here to tilt the GRISM, which kind of optimizes the signal to noise for either the red end or the blue end. So we have that configuration. So I've put in my configuration. I'll put in an exposure. So what do we think here? So it's a 17.9 magnitude object. So any propositions for exposure time here?
600 seconds, maybe.
Yeah.
Yeah, that's a very reasonable exposure time in my opinion.
That sounds reasonable to me, yeah. Yeah. So I'm going to put in 600 seconds. And then I'll add an arc as well. I don't necessarily need the arc. We're not really that worried about precise wavelength calibration, but I'm kind of superstitious. So I always add an arc to everything because I don't think you can have too many calibrations.
So again, like when you're taking spectra, would you normally just take one, or is that just like a time-saving thing for?
Yeah, well, okay. So for that, we actually do the opposite. I almost always get 2 spectra personally with Sprat, and that's because we want to be able to easily distinguish emission lines and cosmic rays without having to go and squint at the 2D spectrum and say what's what. Because unlike with a star, where it's only on a few pixels of your image, or a supernova, and chances are your cosmic ray is not going to hit those. If you have a trace that extends all the way across the CCD, it's going to get hit by a cosmic ray in a 10-minute exposure. There's just no way around it unless you get very lucky. You can remove those using other techniques, but if this is going to go through a pipeline, which is what we do, it's just better to have 2 exposures, and then there's absolutely no doubt about what a cosmic ray is.
But I shall defer to Dan and split this up into 2. I set it up as 1, so I can edit my sequence. So I created that sequence, but I can edit it as well. So I can bring this up. I can click on my exposure here, and I can edit it.
Yeah, I mean, it depends on your science objectives, of course. If you're only aiming to classify something and it's going to be very bright, you're probably not going to be too worried. And the redshift in advance, you're probably not going to be too worried if you lose a few pixels to a cosmic ray.
Yeah, when it comes to classification, I'm probably a bit more cavalier. You know, I take typically take one spectrum, but perhaps that's because you know, I'm looking at sort of galactic objects like CVs and that sort of thing, and in that case,
yeah. In my case, it's also because we share these spectra, and you don't want people emailing you when a cosmic ray shows up in the spectra that you give them. You know, wondering what the strange emission line is, and then you have to explain it to them, and et cetera. So it's just better to be able to be sure you can give clean spectra.
Yeah, very sensible.
There is a signal to noise penalty to pay for that, because spectroscopy is another regime where you are actually often dominated by the read noise instead of the you know, simple signal to noise calculations from the sky. And so the longer you expose, the better your signal is in linear space instead of in square root space. This will make all more sense tomorrow after you do the module.
Yeah, okay, so 2020 RML, which is the unclassified one. So that's got a discovery magnitude of 18.1. So that's in our ballpark. So I might clone that one I just set up.
There's a few more questions in the chat if you have a sec, Chris.
Sure, I should just, let me just finish this. So I'm going to change it to that. I should adjust the exposure times as well. Let's go. Let's go along. Right. Let's look at the chat.
Yeah, so if you scroll back, there's one by Arvind. If they're still online, maybe they can ask their question live.
Yeah.
Yeah, I just wanted to know, like, some of those bright stars in those images, there looks like a black patch on top of them. So.
Sorry, say that again.
So some of those bright stars in those images, there looks like there's something obscuring them. So.
Oh, right. Yes, yes. I think I know what you mean. So, in particular, in some of the ones I took a couple of nights, these Eagle Nebula ones, which is not that one. Let me try again. One of these. Yeah. So you mean these sort of things?
Yes.
Right. So what that is saturation. So here we have a field with lots of extremely bright stars, and these are saturated, and yeah, it looks really weird. But what this is an artifact from the saturation of the CCD, essentially, you know, sort of charge spilling over into neighboring bins and so on. So these Eagle Nebula images, just as a kind of, you know, sort of a teaching tool, I took a series of different exposures. So if I look on, so I took some over 2 nights. So on this night, I took the same field, but with some significantly shorter exposure times. And in this one, you can see that, you know, a lot of the stars, you see most of these, some of these really bright ones, they're still a little bit saturated. But some of the other ones that were saturated in the longer exposures are not. So yeah, so I encourage you to sort of look at these frames. You can look at the observing log, and you can see the exposure time I took in some of these, and you can appreciate the difference. On the LT website, there's an exposure calculator here. So this is this lets you sort of estimate the signal to noise you can get for objects of different brightness. So if I put this in SNR mode, so here we have the exposure time you need to get a signal to noise ratio of 10, 100, 25, 50, and this will be the limiting magnitude to get those signal to noise ratios. So we can sort of play around with this and change the seeing. The seeing gets worse, and so your limiting magnitude also worsens. You brighten the sky, the moon's getting full, and again, you're looking at brighter stars to get the same signal to noise and the same exposure time. And there's a similar calculator down here for spectroscopy.
Thank you.
So I was actually wondering a little bit about that myself. So why, in this case, so most instruments, when they saturate, the saturated pixel is just the maximum pixel value, but here it seems to roll over and go back to 0. Is that just because the amplifier essentially can't handle it and just reads out a garbage value, or what's actually going on in there?
Yeah, I think that's what it is. Yeah, it does look weird. I mean, when I first saw it, I queried it as well. What's even sort of weirder is that you know, sometimes you get in CCD images you get sort of persistence, you know, and in subsequent images you'll see oh, I've lost it again. You'll see yes, this weird sort of you know, diamond shape. I've seen just that shape in a subsequent image where someone has sort of blown out the CCD in a previous observation, you know, just you know, with no star there at all. And then that looks really odd, and you know, that threw me when I first saw it, because yeah, this is not a sort of this is not you know, how on a lot of detectors a saturated CCD looks like. You know, you often get these sort of long trails through the images. I don't know whether it's to do with the way that we read out IO. Now, the way we actually read the chip out has changed over the years, because there's quite a complicated chip, and there's like multiple sets of amplifiers you can read it out. So I'd need to look up exactly what Chris does currently, but we have sort of read it out in different ways to improve the read noise, essentially. So it might be some sort of artifact of that sort of readout and processing that causes these sort of strange shapes. But yeah, they are kind of unusual.
Yeah, I mean, it is a lot better, that, as you say, than you normally see when you have saturation at that level and you have blooming all across the chip.
Yeah, yeah.
So maybe it has some anti-blooming treatment.
Yes.
There are ways to reduce blooming at you know, some other trade-offs.
Right. I'm gonna sort of carry down the questions in the chat, and then maybe after that we'll think about wrapping up. We've got observations still in the queue, and as I say, so we can check in tomorrow, and hopefully we'll have a lot more data to look at. But I think I'm running out of things to say and show you. So yeah, so we've talked about these patches. Exoplanets most excited about. Yeah, we talked a bit about that. So yeah, the TRAPPIST observations were really exciting when that first came out, and you know, we're beginning a sort of a new epoch now of exoplanet observations. Now the test results are coming in, so there's all sorts of proposals we've got active at the moment for people following up test observations. So I think there's going to be lots of exciting exoplanet results coming out in the next few years. The great advantage of TESS and also, you know, Plato, which is a few years away, but the next ESA space mission for exoplanets, is that they're deliberately targeting bright stars. You know, Kepler was hugely successful, but the way it worked, focusing on that sort of single field, was that many of the exoplanet candidates it found were pretty faint for follow-up. Whereas, you know, the new generation, TESS and Plato, you know, they are looking at bright stars all over the sky, with a specific sort of component of the mission being to maximize the potential of ground-based follow-up and exploitation of things it finds. So over the next, you know, 5 years or so, we're going to find huge numbers of actually really sort of bright and interesting exoplanet candidates. So yeah, I think it's going to be, you know, it's going to continue to be sort of a major part of our portfolio. How do astronomers study the rotation periods of stars with the Liverpool telescope? So we don't have, I don't think we have any observers actually doing that sort of thing. You know, that sort of thing is where you need a sort of higher resolution spectroscopy, typically, than what we offer. I mean, our Photospec instrument is an intermediate resolution. It's got a resolution of a few thousand, which can do a lot of things. You know, it's very good for sort of radial velocity work. The main limitation is it's not very sensitive, so we have to sort of concentrate on bright stars. if someone was to give us a big check, I think one of the instruments that our director would like to build would be a new sort of spectrograph of sort of medium resolution, a successor to Photospec, where we could use what we've learned with Sprat, which is a much newer instrument, and build something that's much more efficient and having a much higher throughput. So I've used Frodo in the past for sort of radial velocity measurements of binary stars, typically binary stars with orbital periods of like a few days. And so for that sort of radial velocity precision, it's pretty good. But yeah, we have to focus on bright stuff. It is very precise for sort of this type of work, because it is bench mounted, so it's extremely stable. If you compare it to a spectrograph that's actually mounted on a telescope, there's a lot of flexure in the instrument as it moves around the sky. The telescope moves to different positions. So this is where you're taking arcs to sort of calibrate out that kind of shift in terms of the translation between the pixel position and the wavelength. Which I guess is, this is again something you're going to be looking at tomorrow in the spectroscopy session. But yeah, the great benefit of Frodo is it's bench mounted, it's mounted on the floor, it's extremely stable and sort of very reliable from that point of view. It's just the throughput's not that great. How will we go about making a proposal for LT time? So on our website, there are these details. So there's a phase 1 page. So we have these two phases. So phase 1 is the proposal phase. So you would write a science proposal. And there's information on how you would do that here, and you would submit it when we have a call for proposals. So there are 2 calls for proposals per year. The next call for proposal actually will go out probably in about a week or so's time. So it will be going out beginning of September, and we'll be requesting proposals with a deadline of submission of those proposals sort of early October, first week of October. And then what happens is we collect all those proposals together, and we have a time allocation committee with lots of highly expert people like Dan, who sit on that time allocation committee, and they read all the proposals and they decide which ones are the highest science priority, and they get awarded telescope time. So it's a little bit different to how, like a lot of facilities work. So you wouldn't be awarded a night. So if you were to apply to a lot of telescopes, you would apply for a period of time in the year, and you'd be allocated maybe sort of 1 or 2 nights, and you'd travel to the telescope and you'd observe there. Or if it's a shorter observation, you might be awarded service time, in which case the observatory would take the observation for you. So when you get awarded LT time, you get awarded a certain number of hours, and those hours are yours to use at any point during the semester. So you do exactly what I've done tonight. You would put observations in the queue. The one difference is you wouldn't have this sort of super high priority that I've given myself tonight. So you might queue up your observation, and you might have to wait, sort of 1 or 2 nights for it to be observed, depending on what it is. If it's a high science priority, like gravitational wave counterpart follow-up, and you to put it in, it would be observed that same night because of the sort of priority flag that's been set in the scheduler. But if it's something sort of mundane, like supernova observation, where you need an observation on sort of timescales of days, you'd be looking to get your data back, maybe within sort of 24 hours or 48 hours and that sort of thing. And that would be how you proceed. You'd have a certain amount of time to use over the course of the semester, and you would collect your data, and you would get emails in the morning from the telescope. If you've had any data taken from you, you get an email saying, we took some data for you last night and here it is. And you can download it and look at it and you can use it. So that's how the process works. Fiona says, how much money would you need to make the spectrograph at NRT you were talking about? So, right, so NRT, I'm not going to go into this in much detail because of the, it's getting late, and I think probably everyone's tired. But I talked earlier about we are looking to build a new telescope, a 4-meter robotic telescope will be the successor to the Liverpool telescope, what we're calling Liverpool Telescope 2. So that's an expensive project. The budget for that is about 23 million British pounds. So we've got various sort of funding proposals in. We've got partners around the world who are working with us on this, and we aim to complete the funding consortium and start actually building things probably about sort of April next year. So in any sort of new project, the longest lead time for any new telescope is the mirror. Making the mirror. This is a highly precise piece of equipment. So that takes time scales of years. So we'll be looking to start manufacturing next year with an idea that we'll begin observing with the telescope, what we call first light, around about sort of 2025. So that's one of the major sort of technical activities we're working towards at the moment. And the initial instrumentation on the telescope would be a spectrograph, something along the lines of SPRAT, as we've seen, a high throughput spectrograph, low resolution for transient work, and an imager. So the similar sort of instruments we played with tonight. Again, so question on proposing for LT time. What is the minimum / maximum amount of time you can reasonably apply for? Well, that depends on your science program, really. It's, so one of the chief things that a time allocation committee for our telescope, or any telescope, will look at is the time request justified? So if you have an extremely exciting science topic that requires a lot of telescope time, you can justify in your proposal, then you can apply for a lot of time. So just to give you a sense of the type of the scale we're talking about, so in a semester for our telescopes of half the year, there are 300 hours that are available to the UK community in half a year. There's a similar 300 hours available to the Liverpool John Moore's team. So within Liverpool, we have the same amount of time on our own telescope as the rest of the UK. So that's pretty good. We get a lot of Liverpool telescope time, but then we do own the thing, so that's fair enough. And then the rest of the time in the semester is split amongst various other committees. So for example, there's a certain amount of Spanish time, about 150 hours of Spanish time. And there are international programs we're part of where international observers can gain access. And we also devote 10% of our telescope time to schools observing. So there's thousands of UK and Irish schools who can access the telescope and observe. You know, typically they're observing things like, you know, sort of messier objects and that sort of stuff. But this is our large sort of, you know, outreach endeavour. You know, we put the telescope and access to the professional telescope in classrooms in the UK and Ireland. So that takes a chunk of the telescope time as well. So yes, so for, you know, UK-wide, about sort of 300 hours. In terms of the types of requests we get, the largest requests we get are around about sort of 60 hours in a semester. So if you think about that, that's, you know, probably about sort of 6 to 8 nights, depending on the time of year. And the smallest requests can be, you know, sort of 1 hour, 2 hours. So this is if someone wants a single observation of something, or if they're sort of monitoring something where they need sort of a couple of minutes over, you know, timescales of months. So that gives you a sense of the amount of time that people sort of apply for. Right. Okay, so it's 20 past 11 here now. Are there any final questions I could answer? If not, I think we'll probably wrap things up about now. All right, good. Right, I think I've tired everyone out. So thanks everyone for being with me. I mean, it's been a long day. I appreciate you joining me. I hope you found this interesting, and I hope it's if you've attended both the sessions, I hope it's given you sort of a different perspective on different telescopes and how they work. So do keep checking the data as it comes in. It will carry to coming through the night, and if we look tomorrow, there'll be some spectra on some of these objects to look at, and hopefully for some of these things we can actually get some actual results out there. So a classification and an ATEL for this this unknown supernova, that might be something we can send out tomorrow.
Yeah, and if you're in a time zone where you're not going to bed for a while yet, feel free to take a look at the data and share what you see and any comments in the chat.
Please do, yes, indeed, yes. Yeah.
Well, thank you, Chris.
Oh, thank you. And thanks to Dan for keeping me company, helping out, fielding the questions and so on.
Oh, thank you for leading this.
Okay, right, see you tomorrow.